If you like our content, please like, subscribe, and click the notification bell to get alerts when we introduce new videos.
Access points contain radios that are RF transceivers, radios that can both transmit and receive that use RF signals. When using an external antenna, the RF signal travels along the connected coaxial cable connecting the antenna to the access point. However, not all wireless devices have antennas that you can visibly see. Most APs, laptops, and other devices have internal wireless antennas. The radio and the device receiving the signal is known as the receiver. Since the radios using Wi-Fi are both transmitters and receivers, they're referred to as transceivers. In laptops, the antennas are usually integrated into the bezel around the screen. The transceiver used in modern laptops is integrated into the system board. Older laptops may have had wireless network cards that connected with PCMCIe slots or USB connections. The transmitter receives data for transmission and converts it to an oscillating signal, which is then modulated with the data to be sent wirelessly. When the wireless signal includes the data for transmission, it is referred to as the carrier signal. The power level of the transmitter's amplifier determines the amplitude of the wave, and once placed into the air via the antenna becomes an RF signal. The steps involved in wireless transmission are: the transmitter receives the data to be transmitted. It converts the AC signal using a modulation technique to encode the data into the AC signal. Once modulated to include data, it is referred to as a carrier signal, meaning that it contains the data being transmitted. The carrier signal is sent into the antenna for propagation. The signal is sent out of the antenna at a configured amplitude or power level based upon the properties of the antenna. Antenna function. It is important to know that antennas are bidirectional passive amplifiers and are used in both transmission and reception of RF signals. Antennas are connected to a radio transceiver via an RF cable and convert electromagnetic current into RF waves. The wireless radio then modulates the signal onto an electric current which passes over the RF cable, typically made of a copper core. The current then makes its way to the antenna, which generates electromagnetic waves known as radio frequency waves or RF waves. As we previously mentioned, antennas both send and receive these waves, also referred to as signals when they are carrying data. And their send-receive functionality depends on which way the traffic is flowing. If transmitting, the antenna will place the signal in the air, and when receiving, it will take it from the air and pass it over the RF cable back to the transceiver. When a device transmits data, the antenna takes an oscillating signal from the transmitter and turns them into radio waves, directing them away from the antenna. When the device receives the data, the antenna takes the RF signal out of the air and turns it back into an oscillating carrier signal and directs it back through the RF cable to the receiver. Electromagnetic radiation. Electric and magnetic fields are perpendicular to one another, moving into space away from the source. Electrons moving in a current produce an electromagnetic field. The field produced by an electrical component is known as the E field. The magnetic component produces a field known as the H field. During a transmission, both of these fields propagate away from and perpendicular to the antenna. The E field creates an H field and vice versa. These two fields create a continuous pattern. This pattern moves the electromagnetic radiation through space. Knowing the basics of propagation is important. You may see the antenna chart patterns referencing E field or E plane as well as H field or H plane. These charts give engineers visual representation of the RF wave patterns each antenna provides. For a horizontally polarized antenna, the E plane is horizontal or azimuth plane. The H field and E field are 90 degrees apart, so on the horizontally polarized antenna, as discussed earlier, the H field will be the vertical or elevation plane. Polarization. The term polarization describes the orientation of an antenna's wave oscillations. In vertical polarization, the wave moves up and down like the waves in the ocean. With horizontal polarization, the waves move side to side like a slithering snake. Both vertical and horizontal polarization are linear. Circular polarization has the RF wave move in a corkscrew pattern, which makes one revolution of the pattern per wavelength. If the polarization of the transmitter and receiver do not match, the signal quality is degraded. You can change the polarization of an antenna by changing how an antenna is mounted, such as a fixed antenna or moving and articulating antenna. In addition to placing signals into the air and receiving them, another function of an antenna is to shape the RF coverage. So changing the polarization of an antenna alters the coverage provided. A dipole antenna, or omnidirectional antenna as it's commonly referred to, has a linear polarization. When they are mounted straight up and down, they have a vertical polarization. When they are mounted on their side, as if parallel to the ground, they have a horizontal polarization. When using this type of antenna, you will want to point the coverage where the intended receivers reside versus pointing the tip of the antenna at them as if the antenna were some type of magic wand. This type of antenna has a coverage pattern that resembles a donut or a bagel in shape. So if you point the antenna at a receiver, you are pointing the hole at the receiver and not the RF coverage. The technical name for this type of coverage is toroidal. Passive gain. This image represents an isotropic radiator. An isotropic radiator is a theoretically perfect antenna. It is called a theoretical perfect antenna because a perfect antenna that can send and receive from every side doesn't exist within our current technologies. An isotropic radiator, like the sun, can transmit equal energy in all directions. If it were used as part of a receiving system, it would receive from all directions as well. As you learn in the RF math module, dBi is decibels referenced against an isotropic radiator. In antenna terms, dBi is the term used to reference the amount of gain displayed by real-world antennas compared to an isotropic radiator. Antennas, in addition to placing signals in the air, receiving signals, and shaping coverage, also passively amplify RF signals. This means that they increase the gain of a transmitted or received signal without adding any additional electric current to the signal the way an active amplifier would. The gain of an antenna is created by the elements which make up the antenna, allowing all of them to focus the RF energy in a specific pattern. The gain of an antenna is measured in relative units, dBi or dBd. The antenna adds a fixed amount of gain due to its construction. If you supply more energy at the intended radiator, or supply less energy at the intended radiator, the antenna's amplification factor remains the same. If you have a 10 dBm intentional radiator using a 3 dBi gain antenna, the output will be 20 dBm or 100 milliwatts, as you learned in the RF math module. For every 3 dB gain, an antenna provides not only double the signal strength, but the coverage provided will also be doubled as well. Replacing a 3 dBi gain antenna with a 6 dBi gain antenna doubles the size of the coverage area. Different antenna types produce different coverage patterns. Beam patterns. RF beam patterns have both vertical and horizontal components. They are not always equal. There are also incidental coverage patterns created when using antennas. These are around the antennas that provide unplanned coverage. They are often referred to as rear or side lobes when using directional antennas. The beam width patterns are measured at the point where the power of the main lobe or beam has decreased by 3 dBm, the point where the power is reduced by 1/2. Although beam width and pattern are related, they are not the same. The pattern may be the same for two antennas of the same type, but with different gains. The gain changes the size and, to a degree, the shape of the pattern. A higher gain antenna, for example, will have a narrower main beam than a lower gain antenna. In the field, you will need to use the correct antenna type to provide coverage only in the directions needed in order to reduce interference and co-locate more APs successfully in a high-density environment. Azimuth and elevation. Azimuth and elevation are terms used to describe portions of the RF pattern. The azimuth is a view of the antenna's beam pattern from a top-down perspective. The horizontal image here shows you the 360-degree coverage of an omnidirectional antenna. The elevation is a vertical view from the side of the pattern. This shape will vary based upon the antenna gain used. Lower gain antennas will have a wider pattern, while higher gain antennas produce a narrower pattern. Antenna chart details. When choosing antennas for specific placements and coverage types, you will see that manufacturers publish antenna charts to show what the specific antenna's pattern and beam widths look like. These antenna charts outline the main lobe, side lobe, and rear lobe from a shape and degree perspective. The main lobe is the intended direction of energy, the targeted direction for which an antenna is manufactured and selected by the wireless LAN designer. The side lobe is the unintended direction of energy providing incidental coverage beside the main lobe. It is comprised of escaped energy to the rear and sides of the antenna. While these lobes do provide usable coverage, they should not be planned to do so. They are incidental coverage and not intentional coverage. Omnidirectional antennas are only omnidirectional in name. The small rubber dipole antenna is an example of this type of antenna. It is the default antenna of most external antenna access points. A perfect omnidirectional antenna would radiate RF energy like the sun radiating light in all directions, just like we spoke of the isotropic radiator earlier. These antennas, however, do not radiate RF energy from their tips, nor do they from the cable connector. Therefore, you get what is commonly referred to as a donut pattern. They do, however, radiate and detect energy in a 360-degree pattern around the antenna in their horizontal beam width. The vertical portion of their pattern can be larger or smaller based upon the gain of the antenna. A high gain omni has a smaller or more narrow vertical beam width, while a lower gain omni has a larger or wider vertical beam width. Semidirectional antennas have a more focused beam than omnidirectional antennas. They are used to limit the coverage provided to a more specifically limited space in one direction versus trying to provide coverage in 360 degrees. Patch panel antennas and Yagi antennas are examples of semidirectional antennas. They focus RF waves into coverage patterns of various shapes and sizes, allowing a wireless engineer to provide coverage where it is needed. Panel antennas, also commonly referred to as patch antennas, consist of one or more active elements mounted above a reflecting surface, a ground plane. These antennas are typically used indoors to provide coverage to a specific area, such as a hallway, a gymnasium, or other such areas, where omnidirectional antenna coverage is not needed and can have up to a 180-degree coverage pattern. Yagi antennas are generally used outdoors and at longer distances and typically have up to a 90-degree coverage pattern. We talk about typical use, but in the field you may see Yagis used indoors and panels used outdoors. As long as legal guidelines are being met, both are acceptable. In addition to focusing the RF energy only where it is needed, both of these antennas reduce the likelihood of creating or suffering from interference and aid somewhat in security by helping to contain the signals within the desired areas. Highly directional antennas. These are antennas that have very narrow beam widths and usually very high passive gain. These antennas are more often used for outdoor point-to-point links than they are for any area coverage. However, they may be used to target one or more remote clients in a very specific design as well. They normally have a beam width of less than 25 degrees. Dish or grid antennas are also considered highly directional antennas. They look like a big bowl or a small satellite dish compared to the previous antenna types. They are more susceptible to the effects of wind, which can physically move the antenna, causing a degraded signal or even complete loss of signal. That's called wind loading. Wind is the weather element that most often impacts outdoor bridging, but snow and ice can move antennas too if they have enough weight. However, wind occurs every day. Grid antennas are also highly directional, but are more resistant to wind loading since they allow the wind to blow through them. In some areas where wind or other weather elements, such as ice and snow, create problems, you may want to use a radome. A radome is a non-RF impeding shield around the antenna that will keep the wind and other elements from affecting the antenna. They can also be heated to melt away any ice or snow. When looking to implement dish or grid antennas, indoors or outdoors, the RF line of sight or Fresnel zone is an important factor in determining how strong an RF signal is received for these types of links. It is important to know there are additional considerations when using these types of highly directional antennas. BeamFlex Smart Antennas. BeamFlex is a unique RUCKUS technology and one of the main advantages of using RUCKUS wireless access points. The BeamFlex antenna array directs transmissions towards the client to maximize the efficiency of the transmissions. What exactly does BeamFlex do? It creates dynamic adaptive antennas. With BeamFlex, the physical antenna elements, which act like lenses or reflectors depending upon which ones are turned on and which ones are turned off, are part of the antenna array. This antenna array with multiple elements can be turned on and off in combination with the access point's 2.4 or 5 GHz radio chains using RUCKUS proprietary algorithms. Combined in real time to form thousands of antenna patterns, BeamFlex has no analog adjustment of phase on each radio chain like an in-chip based beamforming. Proprietary antenna control software learns and selects the optimum RF antenna element combinations for each antenna as clients roam on a packet-by-packet basis. This provides unprecedented reliability by providing complete control over Wi-Fi signals and focusing RF energy only where it is needed and not creating additional interference for other clients. Single input, single output, or SISO diversity is used to mitigate multipath and legacy systems. Simple diversity systems maximize wireless range and coverage. They use multiple antennas to increase probability of there being a high-quality signal path. Diversity antenna systems use 2 or more antennas spaced multiple wavelengths apart. They use only one antenna at a time and change antennas only when a received signal is weak or has a poor signal-to-noise ratio. Simple diversity and multiple signal combining techniques can be effective even if only used on one side of a link. Diversity antenna systems are used to improve transmission and should never be used to provide coverage in different directions. SISO diversity was used commonly on systems supporting legacy 802.11a, b, and g transmissions. 802.11n, 802.11ac, and 802.11ax require multiple input, multiple output, or MIMO antenna systems. MIMO diversity uses at least 2 antennas. These antennas are connected to the radio through separate radio chains for each antenna. The radio can send and receive using multiple antennas at the same time instead of just using antenna selection. The enhancement over simple diversity allows for greater throughput. Whereas CISO was used to combat the downfade introduced by multipath, the same signal taking multiple paths to arrive at the receiver due to reflection, MIMO systems take advantage of the multipath signals received in such a way as to create better signal quality or upfade. The receiving radio can include information about the reception of the signals in acknowledgement frames sent to the transmitter. The transmitter uses that information to alter the next sent signal to that station. This process is part of transmit beamforming and is part of the 802.11 standard. BeamFlex Plus is the receive function of a BeamFlex antenna. Whereas BeamFlex describes the transmissions made by a RUCKUS access point using BeamFlex, BeamFlex Plus refers to the improved reception of signals transmitted by wireless clients. The BeamFlex antenna array is designed to minimize the amount of internal electronic noise. This reduction, when combined with the increased sensitivity of the BeamFlex antenna, means that clients are able to transmit at higher data rates. This makes the wireless LAN operate more efficiently. Multiple input, multiple output, or MIMO, added support for multiple transmit and receive antennas per access point and was introduced as part of the 802.11n amendment to the standard. MIMO allows an AP to have multiple streams of data over corresponding antennas to one or multiple stations, providing higher data throughput. Multiple user MIMO, or MU-MIMO, allows for more than one station to take advantage of these spatial streams at a time, allowing more users to be serviced simultaneously. When looking at AP capabilities, you will commonly see the number of antennas indicated as 2x2, 4x2, or even 8x8. This gives reference to the AP's capabilities and outlines data rates dependent upon which PHYs, modulation, and coding schemes are planned to be used. To optimize this, the client devices must support the same functionality.